Hello, it's me, Brody. I'm making another YouTube video because I really want to make sure that when people are surfing the internet, they can find out all about my life and everything I've achieved, and they can watch my YouTube videos and enjoy watching them. I don't think anybody really does watch them very much. I've got moisturiser all over my eyebrows still, which isn't a very good look for me. And I haven't been to the barber for about 2 months, so just been using the ward clippers to shave my hair, which looks pretty abysmal, and is really itchy for some reason. Gross. Anyway, this is a really cool invention that I want some people to support me with. Nobody's probably ever going to, but if you know somebody that wants to steal it or donate it to a good cause, then get in touch with me, and I'll happily assist you with either. Here's an article all about it. It's called The Dawn of Nanophotonic Cloud Infrastructure, Solving the Data Storage and Quantum Networking Crisis. The imminent collapse of legacy data architecture. So the global digital economy is hurtling towards an absolute thermodynamic and spatial wall. The world's data generation is expanding at an exponential, relentless rate, pushing the forecasted £5.44 trillion global cloud computing and storage market towards a physical and operational breaking point. For hyperscale infrastructure providers, titans such as Amazon Web Services, Google Cloud, and Microsoft Azure, the prevailing strategy of relying on sprawling football field-sized warehouses filled with fragile magnetic tape libraries and spinning magnetic hard disk drives (HDDs) is no longer a viable long-term solution. The technological ecosystem has fundamentally outgrown the underlying physical media that supports it. The limitations of legacy storage are dictated by the immutable laws of physics. Magnetic storage media are rapidly approaching the super-paramagnetic limit, a physical constraint where the magnetic grains used to record binary bits of data become so microscopically small that ambient thermal energy can spontaneously reverse their magnetization. This spontaneous reversal leads to catastrophic data corruption and bit rot. To combat this physical limitation, modern era centers require immense energy-intensive HVAC and liquid cooling systems to maintain strict environmental controls. The physical real estate footprint required to house exabytes of data is inherently unsustainable, and the crippling cooling costs required to keep these legacy systems operational are rapidly eroding enterprise profit margins. Furthermore, legacy magnetic tape, the historical backbone of cold archival storage for decades, is inherently vulnerable and highly inefficient. It degrades over time. It's incredibly susceptible to water damage and can be destroyed by relatively minor ambient temperature fluctuations or stray electromagnetic interference. The fragility necessitates a constant, costly hardware replacement cycle wherein massive datasets must be periodically migrated to new tapes every 5 to 7 years to prevent data loss. This constant migration consumes vast amounts of continuous electrical power, mechanical wear on tape handling robotics, and immense operational expenditure. Simultaneously, the global technology sector is standing on the precipice of a second, even more profound revolution, the quantum internet. However, the realization of distributed, hyperscale quantum computing networks is currently blocked by a severe physical bottleneck: superconducting quantum computers. The leading architecture pursued by the world's top research laboratories process information using incredibly faint microwave photons in the same cryogenic environments cooled to a few millikelvins above absolute zero. Because these fragile microwave whispers rapidly decohere and are destroyed by thermal noise at room temperature, they must be converted into higher energy optical photons in the telecommunications band to be transmitted across global fiber optic networks. Historically, the physical act of translating these signals generated too much localized heat, which instantly destroyed the delicate quantum states of qubits themselves. Addressing these dual crises requires a paradigm shift in foundational hardware. Through the convergence of integrated nanophotonics, acoustic optomechanics, and quantum physics, a unified hardware ecosystem known as the Imagenta data infrastructure has been engineered. That was the thing I made. This architecture is designed to permanently mitigate data center power consumption while maximizing petabyte per cubic centimeter data density, concurrently providing the critical microwave to optical transduction required to link isolated quantum processes into a global network. Next bit is called the economics of physics and data storage crisis. So, to understand the necessity of the Imagenta platform, one must examine the fundamental economics of the cloud storage industry. The £5.44 trillion valuation of the cloud computing market is heavily predicated on the ability to store, retrieve, and process data with decreasing marginal costs. However, the marginal cost of data storage has ceased to decline at historical rates because the density of magnetic media has plateaued. When a hyperscale provider builds a new data center, a significant percentage of the capital expenditure is dedicated not to the computation, but to the thermal management of the facility. Spinning disks generate friction and heat. Magnetic tape requires strictly climate-controlled archival vaults. Because the stable glass block proposed by Imagenta is a true cold storage medium, it requires near zero energy for data preservation. This successfully mitigates data center power consumption to a yield up to 95% reduction in electricity usage. The elimination of spinning platters and robotic tape arms removes the mechanical failure points that plague legacy data centers. Furthermore, the glass medium is immune to water damage and ambient temperature fluctuations, guaranteeing a centuries-long lifespan that entirely eradicates the constant, costly hardware replacement cycles inherent to magnetic tape. The transition to this technology is not merely an incremental storage upgrade, it's a foundational transformation of the data center's economic model. By eliminating the massive power draw associated with data retention, cloud providers can reallocate grid power to high-value computational tasks such as training artificial intelligence models or running quantum simulations, fundamentally shifting the profitability of hyperscale business model. The magic glass block, redefining optical cold storage. So to completely replace legacy magnetic tape, the industry must transition from two-dimensional surface recording to fully three-dimensional volumetric archiving. The Imagenta architecture achieves this through lanthanide-doped 3D optical data storage drives. There's some videos on my YouTube channel about this. This technology relies on a monolithic transparent block of highly stable glass or polymer that's densely embedded with highly luminescent, rare earth lanthanide-doped nanoparticles. The concept of using glass for optical storage is theoretically well established, but previous iterations were severely constrained by low data density, slow writing speeds, and the high optical energy required to encode data. In this advanced ecosystem, data is written using a primary femtosecond excitation laser fired deep into the transparent matrix. A femtosecond laser emits pulses of light that last for only a few quadrillions of a second. This incredibly short duration packs a massive amount of peak optical power into a brief window without transferring significant average thermal heat to the surrounding glass material. The high peak intensity of the femtosecond laser pulse triggers two-photon absorption, TPA. TPA is a non-linear optical process wherein two low-energy photons are simultaneously absorbed by a molecule to transition it to a higher energy state. Statistically, the probability of two photons arriving at the exact same spatial coordinate at exactly the same moment is incredibly low, meaning that the TPA only occurs at the absolute ultra-intense focal point of the laser beam. This prevents the laser from altering the glass along the entire optical path, ensuring that the modification is strictly confined to a precise 3D coordinate deep within the volume of the block. This non-linear process permanently alters the localized refractive index of specific microscopic volume and nanovoxel deep within the 3D space of the glass. Because the alteration is physical and structural rather than magnetic, the recorded data is permanent and impervious to the electromagnetic decay that destroys hard drive. So bypassing the Abe diffraction limit with stead physics. While 3D optical storage theoretically offers immense volume by utilizing the z-axis, which is depth of the material, standard optical writing is fundamentally constrained by the physical properties of light itself. Specifically, the size of a focused laser beam is restricted by the Abe diffraction limit. So according to classical wave optics, a laser beam cannot be focused to a spot smaller than roughly half of its wavelength. If a system is restricted diffraction limited writing, the resulting voxels are relatively large, limiting the overall data density per cubic centimetre. To compete with the sheer volume of global magnetic storage, the optical voxels must be radically compressed. To maximise petabyte per cubic centimetre data density, the Magenta architecture fundamentally bypasses the conventional Abe diffraction limit of standard light by integrating simulated emission depletion (STED) physics directly onto the data writing and reading process. Originally developed as a super resolution microscopy technique for biological imaging, STED utilizes two distinct lasers working in tandem to forcefully shrink the effective focal volume of an emitting fluorophore. Concurrently with the primary femtosecond excitation beam, a secondary donut-shaped depletion laser is fired into the matrix. This secondary beam actively suppresses the luminescence of the nanoparticles everywhere except at the absolute infinitesimal center of the target focal spot. In functional terms, the excitation laser attempts to write a standard diffraction-limited spot, but the overlaying donut-shaped depletion laser instantly forces the outer edges of that spot back to their ground state via stimulated emission, preventing those outer edges from undergoing the refractive change index of change. This achieves extreme nanoscale data compression. An apt analogy is attempting to write an encyclopedia on a grain of rice using a bleeding permanent marker. It's physically impossible unless one possesses a magical donut-shaped eraser that instantly trims the edges of the ink dot before it dries, leaving behind only a microscopic subdiffraction point of light. The crucial role of rare earth lanthanide nanoparticles. So implementing STED in solid-state glass for data storage presents a significant materials science challenge. Traditional STED, as used in biological microscopy, requires incredibly high-intensity depletion lasers. If these high-powered continuous wave lasers were fired into a dense glass block to achieve data storage, they would rapidly cause catastrophic thermal damage, photo-bleaching of the active molecules, or even physical cracking of the optical matrix. The Magenta framework solves this critical hurdle, but through the use of highly specialized lanthanide-doped up-conversion nanoparticles. Lanthanide ions such as ytterbium and thulium, dysprosium and europium possess unique f-orbital electron configurations. Because they're optically active 4f electrons are shielded by 5s. Because they're optically active 4f electrons are shielded by outer 5s and 5p electron shells, their electronic transitions are largely insulated from the surrounding chemical environment. This shielding results in sharp emission lines, exceptional photostability, and long excited state lifetimes, making them ideal candidates for dense optical media. When doped into a host matrix, such as sodium yttrium fluoride, these nanoparticles can absorb multiple low-energy near-infrared photons and upconvert them into high-energy visible or ultraviolet emissions through a process known as energy transfer upconversion. For instance, a common mechanism involves the absorption of 980 nanometer photons by sensitizer ions, which then non-radiatively transfer their energy to neighbouring activator ions. This energy accumulation promotes the ions from their grounded state to a higher excited state, resulting in sharp blue luminescence at 450 nanometers when the ions relax. So engineering ion-assisted cross-relaxation. So the critical breakthrough allows the STED to function at a low optical power and thus prevents the glass from melting during the writing process. Lies in exploiting an ion-assisted cross-relaxation between these lanthanide dopants. Cross-relaxation is a non-radiative energy transfer process between two neighbouring identical or different ions. When one ion is in an excited state and a neighbouring ion is in the ground state or a lower excited state, the excited ion can transfer a portion of its energy to the neighbour. As a result, both ions end up in an intermediate energy state. By precisely engineering the doping concentrations within the nanoparticles, such as synthesizing heavily doped and 10% of something I don't understand, researchers have facilitated highly efficient emission depletion written by these ion-ion interactions. When the donut-shaped depletion laser is applied, instead of relying solely on brute force and stimulated emission to quench the outer edge of the voxel, the laser specifically targets and triggers intense cross-relation pathways in the low-lying energy states of the emitters. Specifically, the optical inhibition of the 455 nanometer emissions is driven by the cross-relaxation states to the F whatever else, mathematical algebra. I don't know who put numbers into maths. It's horrible. This precisely engineered ion-ion interaction drastically reduces the required optical intensity of the depletion laser. Studies have conclusively demonstrated that such UCMP configurations can achieve up to 96% depletion efficiency at 455 nanometers under relatively low power, 810 nanometer depletion irradiation. This entirely eliminates the demand for high-power pulse depletion lasers and ensures the thermal integrity of the glass matrix during the sub-diffraction writing process. So orthogonal multiplexing for petabyte density. So by coupling STED-inspired spatial confinement with unique luminescent properties of lanthanides, data can be encoded and multiplexed across several orthogonal dimensions simultaneously. Sorry, I'm on loads of meds at the moment. It's really hard to get my words out. Traditional optical storage like Blu-ray relies on solely 2D spatial coordinates across a few layers. In contrast, the Imagenta architecture leverages highly multi-dimensional parameter spaces. So you've got 3D spatial coordinates. So using the TPA and STED mechanisms, these ultra-small voxels are precisely positioned across hundreds or thousands of vertical layers within the depth of the glass block. Emission colors or wavelengths. By doping the matrix with a variety of different lanthanide combinations, different voxels can be engineered to emit distinct colors upon excitation. A single spatial coordinate could theoretically hold multiple bits of information depending on whether it fluoresces blue, green, or red. Luminescent decay lifetimes. So lanthanides exhibit uniquely long and tailorable fluorescence lifetimes. By measuring the exact microsecond duration it takes for a voxel's glow to fade after excitation, an additional layer of data can be encoded in that time domain. Because this multi-dimensional multiplexing allows distinct glowing voxels to be suspended across hundreds of vertical layers, the theoretical data capacity reaches into the petabyte per cubic centimeter regime. This transforms a single inert glass block into a repository capable of holding the equivalent of millions of standing magnetic tapes, all without requiring a single watt of resting power. The quantum drive, bridging the cryogenic gap. While storing exabytes of classical data densely and sustainably addresses the immediate classical infrastructure crisis, the future of hyperscale computing belongs to the quantum internet. The exponential processing power promised by quantum algorithms will revolutionize the field of field ranging from cryptographically and materials science to complex financial modelling and pharmaceutical drug discovery. However, the scale quantum computing networks and unlock this potential infrastructures providers must seamlessly bridge the physical gap between isolated, localized quantum processors and global room temperature fiber optic networks. Superconducting quantum computers, the current industry standard architecture pursued by entities like IBM, Google, and diverse academic consortia, think and operate using incredibly faint microwave photons. The energy of a single microwave photon is vanishingly small. To prevent the ambient thermal noise of the universe from overpowering these delicate signals and causing rapid quantum decoherence, the processes must be maintained inside massive dilution refrigerators at extreme cryogenic temperatures of roughly minus 273 degrees Celsius. At these temperatures, thermal photons are virtually eliminated, allowing the qubits to maintain superposition and entanglement. However, a fundamental physics problem arises when attempting to network these machines. Because these fragile microwave whispers are highly susceptible to thermal noise and possess energy levels far too low to overcome the losses of room temperature transmission, they cannot travel long distances across standard infrastructure. They must be currently converted into higher energy optical photons, typically in the 1550 nanometer telecommunications band, to be transmitted globally through existing fiber optic networks. This required translation process is historically fraught with engineering paradoxes. Translating low energy microwave signals into high energy optical signals relies on pumping the system with intense optical lasers. Historically, this generated localized acoustic scattering and thermal energy absorption within the transducer chip. In a millikelvin environment, the introduction of even a microscopic amount of heat instantly destroys the delicate quantum state of the surrounding superconducting qubits, rendering the network useless. Overcoming this thermal bottleneck is the single greatest hardware hurdle in realizing distributed, scalable quantum network. So the deep freeze translator, silicon on sapphire transducers. The Magenta infrastructure resolves this critical thermal bottleneck through the deployment of an entirely new class of device, the silicon on sapphire quantum transducer. The core of this technology is a monolithic microchip that physically catches an incoming microwave photon and faithfully maps its exact quantum state onto an outgoing optical photon, utilizing an unsuspended optomechanical ring resonator architecture. To the thermal decoherence challenge in legacy optomechanics. In optomechanical and electro-optomechanical systems, frequency conversion relies on mediating the microwave and optical signals through to an intermediate mechanical or acoustic vibration. To achieve high conversion efficiencies, legacy systems relied heavily on suspended, freestanding structures such as undercut silicon beams, nanobeams, or floating thin film membranes. Suspending the structure in a vacuum physically isolated the acoustic vibration, preventing the mechanical photon energy from leaking away into the surrounding bulk substrate. This acoustic isolation maximized the mode overlap between the light and the sound, boosting the theoretical conversion efficiency. However, this mechanical isolation came at a catastrophic thermal cost. Because the structure was physically suspended and attached to the rest of the chip only by tiny tethers, there was virtually no physical pathway for the heat to escape. When the intense optical control laser illuminated the suspended device to facilitate the conversion progress, inevitable parasitic optical absorption caused the suspended silicon structure to rapidly heat up. In a cryogenic environment, this lack of thermal dissipation caused severe thermal decoherence. The localized heating radiated the thermal photons and the photons back into the dilution refrigerator, destroying the delicate quantum states of the nearby superconducting processes and flooding the conversion process with thermal noise. So you've got sapphire heatsink breakthrough. So the engineering genius of the Magenta transducer lies in the deliberate replacement of standard silicon on insulator, SOI, wafers with a crystalline silicon on sapphire substrate. Sapphire acts as a massive, highly efficient thermal heat sink, providing unparalleled thermal dissipation at extreme cryogenic temperatures. Extensive research confirms that the cryogenic thermal conductivity of sapphire remains exceptional even at sub-Kelvin temperatures, where the photon mean free path can approach the physical dimensions of the crystal itself. Furthermore, when subjected to extreme thermal cycling from room temperature down to 4K or 5.5K, the bonded interfaces between silicon and sapphire remain structurally intact. Although the two materials possess different coefficients of thermal expansion, precise control of the surface flatness and the thermally grown oxidation layer on the silicon surface allows the bonded samples to survive repeated thermal cycling while maintaining their structural and optical integrity. Because the sapphire substrate can aggressively draw heat away from the silicon wave drive, the SOS quantum transducer does not require a suspended arc structure. The silicon wave drives can rest directly on the sapphire bulk. This allows for the construction of an unsuspended architecture that entirely mitigates unwanted acoustic scattering, prevents uncontrolled signal loss, and absolutely protects the cryogenic environment from optical heating. The heat generated by the optical pump laser is immediately wicked away into the sapphire sink, keeping the local temperature at the millikelvin levels required for preserving superconducting qubit states. So the physics of triply resonant intermodal Brillouin scattering. So to facilitate the actual translation of the photon, the SOS microchip employs a triply resonant three-wave mixing process, specifically resonantly enhanced intermodal Brillouin scattering. This mechanism relies on the coherent coupling between distinct optical spatial models and travelling acoustic phonons within the integrated silicon waveguide. So the process unfolds through a meticulously engineered electro-optomechanical sequence that bridges electrical, mechanical and optical domains. So first of all, you've got the electromagnetical conversion. The transducer utilizes an integrated piezoelectric zinc oxide layer with a precise thickness of 280 nanometers. An interdigital transducer is fabricated with this film with a period of 2.85. When I don't know what 2.85 of what, I'm not a physicist, I just don't know. When the incoming faint microwave signal from the quantum computer hits the IDT, the piezoelectric effect of the ZNO converts the microwave's photons' electrical energy into a confined acoustic mechanical vibration. Specifically, it generates an acoustic love mode with frequency of 2.2 gigahertz. Acoustic confinement via love modes. A love mode is a specialized surface acoustic wave that features a dominant shear displacement field with an asymmetric profile. Crucially, silicon waveguide resting directly on this sapphire substrate naturally supports this confined acoustic love mode without needing to be suspended. The significant acoustic impedance mismatch between the dense silicon range and the underlying sapphire substrate acts as an acoustic mirror, trapping the LO mode within a silicon waveguide. A phononic waveguide taper seamlessly funnels this acoustic wave from the wide excitation region down to the much narrower optomechanical ring resonator. So then you've got optomechanical conversion. So simultaneously, a strong optical control laser pump illuminates the silicon beam. Inside the optomechanical ring resonator, which features a 50 bending radius, the acoustic love mode co-propagates with the optical pump. Through the photoelastic effect and moving boundary forces, the acoustic phonon interacts with the optical pump, shifting its frequency and its spatial mode by Brillouin scattering. This interaction seamlessly embeds the exact quantum state of the microwave photon into a newly generated outgoing optical photon. The phase matching and the interaction Hamiltonian. For this three-wave mixing to occur efficiently, the system must maintain strict resonant phase matching conditions. The SOS OMR is expertly designed to support a triple resonance, meaning two travelling photonic modes and one resonant photonic mode are simultaneously travelling and overlapping within the ring. The travelling waves must simultaneously satisfy both wave factor, momentum matching, and frequency, energy matching. So wave factor matching is like an equation which represents the frequencies of the two travelling photonic modes. In the specific geometry of the Imagenta OMR, a silicon ridge waveguide with 330 nanometer height, 800 nanometer width, and 82 degrees sidewall angle, these modes correspond to the symmetric mode and the antisymmetric mode. Variables are their respective wave vectors and represent frequency and wave vectors of the acoustic love mode. The antisymmetric profile of the love mode is perfectly suited to mediate the coupling between the symmetric TE and the antisymmetric optical models. When the system is driven by a coherent microwave signal, the quantum information can be mathematically described by an interaction Hamiltonian. I don't know what that means, neither does most people, but if you do, then get in touch. Where the annihilation and creation operators of the phononic modes and represent the annihilation and creation operators of the photonic mode is the vacuum optomechanical coupling rate defined by the physical overlap integral of the participating modes. When the strong optical pump is applied, the Hamiltonian is linearized, yielding an effective beam splitter type interaction Hamiltonian. Where that equation is the dramatically enhanced optomechanical coupling rate, this beam splitter interaction is pivotal for high fidelity quantum transduction. Unlike parametric down conversion processes, which can amplify the signal but simultaneously introduce excess thermal noise, the beam splitter Hamiltonian ensures a direct, coherent one-to-one state transfer between the acoustic photon and the optical photon, rigorously preserving quantum fidelity. Furthermore, the travelling wave of dynamics of the intermodal Brillouin scattering naturally decouple the Stokes and anti-Stokes processes. In traditional single-mode optomechanical cavities, both processes can occur simultaneously, leading to parasitic down conversion. By utilizing distinct spatial modes, the intermodal scattering ensures that the energy only flows in the desired direction. This eliminates the need for bulky on-chip or non-reciprocal devices such as magnetic circulators and narrowband filters to separate the pump and signal waves, drastically reducing the physical footprint and complexity of the photonic circuit. So, verified performance metrics. The foundational viability of this architecture is rigorously supported by recent peer-reviewed literature, most notably the 2025 breakthrough by Chen et al., published in Science Advances working with the unsuspended SOS optomechanical ring resonator. Researchers recorded exceptional performance metrics that validate the technology for immediate hyperscale deployment. If you understand any of that stuff, let me know on the postcard. These metrics conclusively prove that strong nanoscale photon-phonon coupling is entirely feasible on a solid, highly thermally conductive sapphire substrate without sacrificing thermal stability. Then you've got scalability, the VLSI integration, and the hyperscale endgame. So the development of high-density STED-enabled optical cold storage and cryogenic SOS quantum transducers represents a massive leap in theoretical physics and materials engineering. However, the translating isolated device physics into global infrastructure requires an absolute industrial scalability. Until recently, quantum transducers and specialized nonlinear photonic circuits have been bespoke, handcrafted assemblies fabricated in university clean rooms. This created a severe commercial bottleneck that prohibited the mass implementation required to build a standardized quantum internet. Imagenta has resolved this commercial bottleneck by ensuring that the silicon on sapphire transducers are fully compatible with standardized very large scale iteration, that's VLSI, semiconductor manufacturing processes. The entire electro-optomechanical circuit can be reliably fabricated on a 200mm silicon on sapphire wafers utilising established industry standard CMOS compatible foundry protocols. This transition from artisanal quantum physics experiments to standardized semiconductor manufacturing offers highly cost-effective, reproducible scaling for global quantum computing networks. And you've got wavelength division and multiplexing for quantum networks. So further accelerating the scalability of this infrastructure is the inherent broad bandwidth of the optomechanical ring resonator architecture. Because the OMR is engineered to support multiple photonic resonances across a wide spectrum of the telecommunications band, the device natively supports multiple optical drive channels simultaneously. This structural advantage enables wavelength division multiplex operation. In a classic fiber optic network, wavelength multiplexed WDM, whatever that means, revolutionized bandwidth by allowing multiple distinct data streams to be transmitted simultaneously over a single optical fiber. Utilizing different wavelengths or colors of laser light, by bringing the WDM capabilities directly to the quantum transducer layer, a single integrated SOS microchip can simultaneously process, entangle, and translate states from multiple superconducting qubits, routing them into different optical frequency channels for long-haul transmission. This drastically reduces the number of physical transducers and optical fibers required to network an advanced multi-qubit quantum processor, accelerating the deployment timeline for distributed quantum architectures and significantly lowering the barrier to entry for hyperscale providers. The strategic value proposition for cloud providers. By deploying nanophotonic optical cold storage and the SOS quantum computing backbone in tandem, hyperscale titans like Amazon, Google, and Microsoft can execute a comprehensive, highly lucrative infrastructure overhaul. On the classic data storage front, systematically replacing millions of failure-prone mechanical hard drives and highly vulnerable magnetic tape libraries with passive, zero-energy lanthanide-doped glass blocks frees up vast amounts of capital expenditure previously allocated to HVAC cooling systems, robotic maintenance, and ongoing hardware replacement cycles. The massive reduction of the physical data sensor footprint via petabyte level volumetric density reclaims prime highly expensive real estate in high density urban technology corridors. This reclaimed capital and spatial footprint can then be aggressively redirected towards deploying the massive quantum computing clusters required for next generation machine learning, molecular simulation, and advanced cryptographic services. The Imagenta hardware ecosystem guarantees that when these highly sensitive quantum processors are brought online, they will not exist as isolated computational silos. They'll be seamlessly linked into a global fiber optic quantum internet utilizing robust, thermally safe, and fully CMOS scalable SOS transducers. This comprehensive ecosystem is not merely an incremental upgrade to existing technology, it represents a definitive foundational strategy to eradicate legacy storage vulnerabilities, solve the cloud industry's crippling thermodynamic cooling costs, and absolutely future-proof hyperscale infrastructure against the exponential influx of global generation. In conclusion, the core subsystems of the Imagenta data infrastructure, ranging from resonantly enhanced intermodal beryllium scattering in silicon waveguides to the extreme nanoscale compression of lanthanide-doped inspired optical data storage, are deeply grounded in established, heavily vetted peer-reviewed literature. The fundamental principles of piezoelectric microwave conversion, extreme thermal management on sapphire substrates, and subdiffraction volumetric data multiplexing have all been validated in rigorous experimental settings. The primary remaining engineering challenge lies in the system-level integration of these distinct, highly specialized components into a singular, fault-tolerant, fully scalable hardware ecosystem capable of immediate, uninterrupted deployment within the commercial hyperscale cloud environments. While the individual device physics is proven and secure, Full end-to-end demonstrations at the sheer scale required by global data center operators remain the focus of ongoing future work. The project is still in its early stages, but I'm very interested in anyone who wants to collaborate on this or get involved in any way. My name is Brodie McLeod. All my contact details are available on X and Facebook, and my direct phone number is just there. I don't understand the physics because I'm not a physicist, but I understand how it works and what it does, and how I got to that conclusion. But I haven't got the physics knowledge to explain what all of those symbols mean, unfortunately. But on the bright side, nobody cares, and I hope you've watched this video and enjoyed it. Thanks.